So this section we're going to focus on the general aspects of cancer and the pathophysiology of it. You also have a separate section of just male and female cancers that go into more specifics related to those. You can start with either one. This one makes it a little bit easier to understand. Alright, so when we're talking about cancer, some basic definitions that are easy for lay people to mix up, right, but are important whenever we're talking about patho to understand the differences of. Alright, so first off, there's usually a tumor. Alright, so a tumor is an abnormal growth of cells or tissue. Right, it can either be benign, meaning non-cancerous, or malignant, meaning that it's cancerous and can spread. Tumors have no function, right? They arise because there's something that has shut off cellular regulation. So we have this unregulated proliferation of cell growth that forms a tumor. Now, they can be benign or malignant. Benign means that the tumor is non-invasive and that it doesn't threaten somebody's health or life. Malignant means that the tumor is going to infiltrate, cause damage, risk metastasizing or spreading, and can eventually cause death. Cancer is whenever we have malignant tumor or tumors in somebody. And metastasis is whenever the primary cancer site has now spread to another part of the body, right? It can either be adjacent or it can travel via different systems like our blood vessels or our lymphatic system most commonly to other areas of the body and then grows tumors there. To name the cancer, if you break down the name, it will tell you what cancer type it is based on what type of cells they are and what kind of tissues they're invading. So sarcoma is going to be cancer that is invading connective tissues such as muscle and bone. Carcinoma is any cancer that arises in epithelial cells, alright, such as breast cancer, skin cancer, or adenocarcinoma, usually associated with things like colorectal cancer. Emia is wherever we have tumors or cancer of our blood-forming tissues. Those are like your leukemias and things like that. Lymphoma is when we have tumors of our lymphoid organs, like our lymph nodes, spleen, or thymus. Some differences between cancer cells. Right, if a tumor is benign, those cells tend to grow very slowly. They're contained in a well-defined capsule. They don't invade other tissues. They're well differentiated, which means if we look at them under a microscope, we could still tell what kind of tissue they originally arise from. We can kind of follow their history. They have a low meiotic index. That means they don't divide or reproduce rapidly, and they don't spread or metastasize. Malignant cancer cells are the opposite. They tend to grow quickly. They are not encapsulated. That's how they can invade tissues and other structures. They're poorly differentiated, which means they look like themselves, but you can't tell what tissue they originally arise from. They have a high reproduction rate or a high meiotic index, and they do cause metastasis. In order for cells to convert to cancer cells, you have to have these hallmarks of cancer occur. Alright, so for instance, a cancer cell had to have gone through all these different changes. Right, at any point in time, our body should be able to shut these down and keep them from going on. When they don't, and it makes it through the whole circle of these steps, then they convert over to cancer cells. For instance, they're not sensitive anymore to anti-growth signals. They don't know when it's time for them to die off and be replaced. Right? They also make their own growth signals. So they tend to grow out of sequence, or they tend to overgrow their area to form tumors. Cancer also needs to have its own blood supply in order to metastasize. That's called angiogenesis. Right? They evade our immune system because they were originally our cells, right? And they've mutated. So since they evade our immune system, then they sneak through our surveillance mechanisms and we can't shut them off, right? They tend to suck up more nutrients since they grow quicker than the tissues that they invade. Alright, so they cause metabolic stress and oxidative stress to our body, alright, and that's how they damage other cells and make people sick as well. Alright, their DNA is damaged. Alright, eventually they will invade or metastasize the body. Alright, and they can have limitless reproductive potential if we don't figure out how to treat them and cure cancer. So let's talk about genetics. I'm sure you have probably had somebody in your family tree who's experienced cancer, and as we do more and more genetic research and cancer research, we're finding more links. Right, so cancer cells tend to have to undergo genetic or hereditary changes as well as epigenetic changes to overcome all of our checks and balances and go through these hallmarks of cancer stages. Right? If we have a genetic predisposition for cancer, it's often our epigenetic, or the things we're exposed to during our life, that will either trigger cancer to begin, to happen sooner than normal, or to stay at bay. Alright, oftentimes it's an interplay of somebody's behavior, their genetics, their environmental situations and work that puts them at cancer risk. So we need to consider all of these. So for instance, maybe in somebody's family tree, they have a history of cancers, right? And then that would be their heredity genetics, okay? So they're predisposed risk for it. Now, say they decide to smoke and not exercise and they're obese, right? They are more likely, from those epigenetic factors, right, those things that they expose themselves to during their lifetime, to speed up the occurrence of their cancer occurring. Right, so that's kind of an example how they interplay with each other. So genetics in cancer, we look around and we see there's usually 4 to 7 key alterations that drive gene cells to change. Right? This has to happen in order for them to develop into full-blown cancer. Our genetics tell us that we're predisposed, that it can happen. Right? The more hits or the more epigenetic exposure we get to carcinogens makes that move faster through these steps. Right? Each hit is going to speed up the growth potential for cells to go through those hallmarks and change to cancer. So for instance, here's the steps, kind of what we're talking about here. We have normal cells, right? Their DNA predisposes them to be able to mutate to cancer, right? During a lifetime, these cells have been exposed to carcinogens, and eventually one of them converts, right? That cell, now remember, it's going to replicate quicker, right, because it's abnormal, and it's going to have faster cellular proliferation. Alright, so it divides and makes more precancerous or more abnormal cells. Those cells are then more likely, with more epigenetic changes and exposure, to convert and keep changing. Alright, and then they change, right? And then we have our final mutation, alright, and they convert over to cancer cells. And then more and more of them are going to form a tumor as they keep growing rapidly. Age is our biggest cancer risk factor. Naturally, as people get older, our defenses of our immune system, of helping the body defend against cancer, get weaker. Alright, and as we get older, we accumulate more hits on our cells over time. Alright, you're just exposed to more the older we are than infants and children. Alright, so that's why as we get older, people are at more risk. Okay. There's different gene types that play an important role in our risk factors. Alright, there's particularly proto-oncogenes and tumor suppressor genes. Alright, so cancer is a disease, no matter what kind it is, of unregulated cell growth. Proto-oncogenes' job is to encode proteins that play a role in promoting cell division. Alright, normally they only signal cells to divide and replicate under appropriate conditions. Like if a red blood cell gets worn out, loses its oxygen carrying capability, the body signals, you know what, you need to die off and go away and I'm going to replace you. That's done by proto-oncogenes. Alright, oncogenes drive chemo or drive tumor growth even in inappropriate conditions. So even if the body says, we have enough of these cells, shut off, proto-oncogenes are going to say, keep going. It's like the accelerator stuck on a gas pedal of a car, right? It sees that there's a tree in front and you should stop the car, but oncogenes are like the gas pedal being stuck down and they won't stop, right? Tumor suppressor genes' job is to prevent unregulated cell growth. So they travel around and they essentially shut down these oncogenes, right? If tumor suppressor genes are deactivated or erroneously inactivated because they've had a mutation, right, then they're not able to prevent unregulated cell growth, right? And that means that like the brakes are stuck, right? The brake lines are cut and you can't stop. So tumor suppressor genes are brakes to cell division, right? Oftentimes if we have cancer, it can be linked back to the fact that something has inactivated our tumor suppressor genes. So nothing is shutting down unregulated cell growth, and then they can keep moving on to cancer development. We had 2 copies of the genes, one from mom and one from dad, right? If we inactivate both of them, right, that's whenever we can end up with tumor growth in our inactivation of tumor suppressor genes, right? So for instance, the genetic mutation, BRCA1, that we see in breast cancer and other female cancers, does this, all right? It shuts off the tumor suppressor genes from both the mom and the dad, so then that individual does not have any regulation for over cell growth in their body. So it's more likely for cancer to occur. Okay. So for instance, Angelina Jolie, she tested positive in her genetic testing for the BRCA genes, and she decided to prophylactically go through a double mastectomy in order to remove her breast to limit her risk of getting breast cancer. Angiogenesis is whenever a abnormal cluster of cells that is trying to form a tumor now recruits a blood supply. Right, what happens is this is a big milestone in the cancer development. Now this tumor, right, it can invade, right, it can pick up nutrients and oxygen from the blood supply, so now it has a lot more potential to grow, right, and it can also send cells out of its tumor, right, it's not going to be localized anymore, into the bloodstream and use that as a conduit to travel to different parts of the body and spread cancer to other areas or metastasis. So metastasis is the spread of cancer from our original tumor to distant sites in the body. This is a complicated process and not all cancer cells can accomplish this, right? But when it happens, it means our cancer is much more complicated, right? So you can do it by a couple of different steps, right? There's direct tumor extension. That's where the tumor is now not encapsulated. It's invading tissues or structures, has a blood supply surrounding it, right? Next, we go through local invasion. The tumor is going to recruit macrophages and reprogram them to lyse or cut through the connective tissue, right, and break out of its capsule so that it can send cells and spread itself throughout the body. Right, the tumor cells must lose cell adhesion through this lysis process in order for them to break away from a tumor. If they have angiogenesis to occur, then they break away, travel into the blood supply, and use that blood supply in order to give them nutrients to fuel their own growth. The last part is metastasis, and this is where they spread distally. Right, the cells invade the blood supply and the lymphatic vessels. They slip out of the tumor and into these. They can adhere to the side of blood vessels when they get to distant sites and then slip out of the blood vessel into those surrounding tissues. And if they're in a tissue that's compatible with their needs, they will grow a new tumor in a different environment. Right, this is just some images or diagrams of how that happens. So we have our primary tumor. There's macrophages that recruit to break this wall down so cells can slip out, get into the blood supply. All right, and then they can leave the blood supply and start another tumor somewhere else. And for instance, this is how we often see spreading of different types of cancer. All right, we'll pick up next with epidemiology.